Ba-boom!
Okay.
All right, so let's keep going. Light is very strange stuff. Light, and when I say strange, it behaves in ways that we don't expect it to. When you look at it closely, when you look at it at small scale. So today we're going to look at the interaction of light and matter when light hits stuff. Okay, is good?
Yes.
All right, let's start talking about clocks. At Buhack Colony High School, they have digital clocks. Kids can't tell time.
Oh my gosh, really?
Yeah, they have digital clocks. It was ding, ding, ding. And
wow.
what that is it's discrete steps. It's this minute or this second, and it doesn't show anything in between. We have an analog clock here at Golden Valley. Our students learn how to tell time using those. Believe me, they want to know when that period's going to end. And some of them are really good with getting the second hand just right. So
sure do.
Analog versus digital, continuous versus discrete. And there are advantages and disadvantages to each. There's more information here because it's continuous, but this is clearly one thing or another. But with the idea of uncertainty in measurement, there's uncertainty here and less uncertainty here. But discrete steps infer exact quantities, like climbing the bleachers. There's a certain number of steps, and if you go halfway, you're not going to go up.
Yeah.
Okay, so those are called quanta. Each one of those steps are called quanta. Quantum. Things that are quantized. Mass is quantized,
Electric charge, that's what I was thinking.
Well, the atomic mass, is the sum of the protons and the neutrons. Electric charge is quantized. People are quantized.
Yeah, I can't have half a person.
Yeah, and so there are a number of things that are quantized. And let's get, this guy was I don't understand his mathematics. It's one of the great holes in my understanding. James Clerk Maxwell showed that accelerating, oscillating charges emit light. He was doing, taking a look at electricity and magnetism and doing experiments and writing calculations, writing equations that would describe the phenomenon that he saw. And in this calculations, the speed of light jumped out.
I thought we just talked about the fact that it didn't.
No. What in his calculations?
Oh, in his calculations,
where there was the speed of light was in the calculation. So.
Oh, I see. It appeared.
Yeah. And so he showed that where does light come from? It comes when charges accelerate or when they oscillate. When charges oscillate, they emit light.
Yes. Mother fluffer. Double tap. There we go.
Now, why do very hot things emit light? Here we are looking into the toaster oven.
Yes, our friend the toaster.
Why do they emit light? If light is emitted by charges in motion, why do hot things emit light? Well, what does it mean to be hot?
Moving.
Yeah, it's the kinetic molecular theory. Our particles are in constant motion. And so the idea is that if they're in constant motion, you've got electrons that are oscillating back and forth.
Yeah.
They're emitting light.
Okay, yep.
Why does the color of light depend on how hot the thing is? The blacksmiths can tell how hot metal is when they're beating on it by looking at the color.
Yeah.
It goes from a dark cherry red all the way up to orange and yellow and bright yellow and white hot. So there's what would be the difference between 1200 degree Fahrenheit that's emitting this color light and 2200 Fahrenheit metal that's emitting this light? Well, it must have to do with how fast they're vibrating.
Yeah, the energy of how much.
Yeah. So it can be observed that the wavelength is inversely proportional to the temperature. Now, what do you mean?
Oh, so shorter wavelength, higher temperature.
Shorter wavelength, higher temperature.
Okay.
Which means
Lower
higher frequency.
yeah, higher frequency. That's what I was thinking about.
No, but that's a good connection to make. So, and let me do this.
And I'm thinking about the colors of.
So if you have high energy, you have higher
Frequency.
If you have higher energy, you have wavelength.
Shorter.
You have a shorter wavelength.
Yeah. That makes sense. I always think frequency and energy, they're always like, in my mind, they're like the same thing.
And that's a good thing.
Yeah.
That makes it very simple. Now, this is a black body radiation, Planck.
There's definitely stuff on this.
Black body radiation. If you have something that's hot, it emits a range of wavelengths.
Yeah.
Okay. And here's something 1,000 Kelvin, and it's got a peak right here. If you go up to 4,000 Kelvin, you get a peak right here. And what is happening is you're getting short as the temperature gets higher. You're getting a spectrum of waves emitted, and the maximum is going to higher and higher energies. Here's 9,000.
Got it. And that makes sense with the equation over there.
Can't read this. 3, 4, 5, 6,000 kelvins.
Yeah.
And so in the visible spectrum, as the temperature goes up, you get more and more of the Roy G. Biv for the visible spectrum. Okay. Now you've also got this other stuff. This is the infrared spectrum, and this is ultraviolet.
What do you mean more of the the intensity over there? Is that what that says?
Yeah, this is the intensity.
Yeah.
And what that is, it's the
more
predominance of a particular.
Yeah. It's more intense.
Yeah. Okay.
Blank.
Now this is before.
My God, what is that? That hair is.
No. Said that the energy of oscillating charges is not continuous. And he said that the energy is quantized. He said
like a
the
digital
energy,
clock.
like we said over here, the energy is proportional to the frequency.
Yeah.
Energy is proportional to the frequency. Higher frequency, higher energy. But there's a connection between this that establishes that only this n is an integer number, 1, 2, 3, etc. It's not continuous, it's quantized.
Yeah, I am
And
familiar with that.
This is Planck's constant. I'm going to write this down. That's
Haven't used that for a minute.
10 to the 34. 6.6 times 10 to the negative 34.
Yeah, negative 34
Negative
joule
34
seconds.
Joule seconds. And what is the symbol for Planck's constant? This is.
Ooh, is it the with like a 0 with a thing through it?
It's H.
Oh, wrong. No, I was thinking of phi.
Oh, we'll get there.
Yeah. Oh yeah, it's up there. Look, H. You had it in the equation.
Where are my glasses?
Yeah. Whoops.
Okay, so photoelectric effect. What happens? Light shining on clean metal can eject electrons. They won't always, but they will, for particular frequencies and wavelengths, eject level. How could you tell that electrons are coming off of something? This is called a photoelectric tube, and what you've got is you have a plate of polished metal and an evacuated tube where there's no air in there, so that if electrons come off, they don't whack into air, and you attach it to a battery where this is the positive side and that's the negative side. So as they come off, they'll be emitted and go over here on the collector plates. You've got the emitter and the collector plate, and then you have an ammeter that basically counts how many electrons, the current. Okay? So if you can measure the kinetic energy of the electron. And then you have the frequency of the light that's coming in. Low frequency, high frequency. Low energy, high energy. And so if you start graphing for the particular frequency of the light and the kinetic energy, the average kinetic energy of the electrons that comes off, there's a straight line 1-to-1 correlation
Yeah.
where the slope is.
Thanks.
You know what?
It says
keeps-
H?
Yeah. Hang on a second. I'm a little stupid here.
Let's write that one down too.
E equals HF.
NHF.
Yeah.
Oh, the N just being the
Yeah,
quantum.
I'm doing that, just leaving it out for a moment here. And so what we've got is we've got
E over F.
energy
Oh, okay.
over frequency.
Oh, I see. I was like, okay, if that's the slope,
H
then
equals energy over frequency. And this
there we
is
go.
how-
There we go.
This is
Oh,
how
sorry.
Planck's constant
I didn't catch that earlier.
was established, okay? But here's the thing. It got down to a particular frequency.
That's an F.
And then you got no electrons.
Yeah.
You got no electrons.
Oh, there's that phi thing that I was talking about. Is he?
Yeah, yeah, that's called the work function.
Oh, that's what it is. The work function. Okay. Okay.
Okay, the brightness of the light has no effect on the energy of the ejected electrons.
Okay. It's all about the frequency.
Yep, only the frequency, only the color of the light, only the frequency. You can have very dim light, and electrons will be emitted.
Yeah.
Not very many.
I that is I recall that. You know, that's
Yeah.
it's a good thing.
So
Okay.
let's go to why Einstein got his Nobel Prize. 1905, he connected the energy of the source with the energy of the light. Wait, what? He said that light is emitted as massless packets of energy called photons.
A photon.
And the energy of the photon is equal to the frequency of the photon. So that's, he established that, and since there were only allowed energy levels had to be quantized, then this meant that the individual photons would have a particular amount of energy
Yeah.
based on their frequency.
Yep. Okay.
Okay, now the question is, how hard is it to pry an electron from a metal?
It takes work.
It takes work, and that phi is the work function. So you've got light coming in, and some of the energy of the light is used to pull the electron out.
Yep.
And then whatever energy is left, that's the kinetic energy of the electron.
Okay. Yeah. Mm-hmm.
So electrons pop off the surface with some kinetic energy that can be measured.
There was a question on work. There was a question about phi on the test.
Here it is.
Yep.
So here's the energy of the incoming photon is equal to
Oh yeah.
the work function, how much work you got to do, and then whatever energy is left over, that's the maximum energy of the electron that comes
Yeah.
off.
That makes sense. Which is also equal to Planck's constant times the frequency of the photon. Okay. Yeah.
Yeah. So that's basically the photoelectric effect.
Okay.
All right, so now let's, you know what, I'm going to put this over here. Energy of the
Work or the photon.
photon.
What is that?
I don't know. It looks like Y is
E.
equal to phi plus max. This is of the electron, which is equal to H times the frequency of the photon.
Is it a 4? Is it a Y?
I know.
We'll never know.
No, I can't do it. All right, what is a volt?
A volt is a joule per charge.
You're talking about the units.
Oh.
That's true. If you're talking about units, a volt is a joule per coulomb.
Oh yeah.
But what is a volt? It's a unit of electrical potential difference.
Yes.
It's the difference in electrical potential energy from one place to another. What is an electron volt? That's what we want to find out. Well, a volt is a joule per coulomb. That's, or I should do it like this, delta V, hello. Delta V is energy over charge.
Yeah.
Okay, so in fact I'm going to do this. Energy over charge. What's an electron? Well, electron is a charge, right? So an electron volt is a unit of energy. Electron
Oh,
volt.
yeah, I see. Oh, yeah. I think we talked about that before.
Yeah.
Dang, energy is just like all the things because we just got finished talking about how it's a kilowatt hour too.
Well, it's like anything else. You use the units that are appropriate for your situation.
Yeah. So.
Okay, so the ejected electron that comes off the metal surface when hit by a photon is called a photoelectron, and it has some kinetic energy. We've already talked about this. The stopping potential is the voltage that just cancels out the energy of a photoelectron. The what? What?
So how much it would
Stopping
take?
potential. What? Wait a minute. Okay, here you've got your metal plate.
Uh-huh.
And here is the photon that comes in, strikes this, kicks out an electron. The electron goes from the anode to the cathode, from the negative to the positive with some kinetic energy. Okay, so what you have here is a stopping voltage adjust. In other words, what you want to do is you want to make this negative and this positive very slowly until for the same amount of light, you get less and less electrons make it over here to the cathode because it's getting more and more negative.
Okay, yeah.
And this is more and more positive. And that stopping voltage is where the electrons no longer don't have enough energy to overcome the potential difference.
Yeah.
So that's called the stopping potential.
Okay.
Is the voltage that just cancels out the energy of a photoelectron. So this is back when I taught this, when this was part of, we would have to solve for the stopping potential. It's just the kinetic energy divided by the
charge.
Yeah, the charge. And that's it. All the important stuff we've covered.
Yeah.
For the photoelectric effect.
Okay.
So
I think the biggest, I think